Hello and good day to all of you. So in this video lecture, we are going to learn about the Kepler's law of planetary motion. So we have looked at the planets and how they are revolving around the sun. So now we will be focusing what are the basic laws of revolving these planets through the Kepler's law. So before starting the lectures, there are some learning outcome of this part of lecture, or the objective you can say. The first objective of this lecture is to understand the Kepler's law of planetary motions, how the planets are moving with a constant relationship between sun and the planets. And the second objective of this lecture will be to explain through the graphical example of the planets' movement and their relationship, how they move around the sun. So let's start with the Kepler's and its law. So first let's look at the Kepler's. Who was the Kepler? Actually, in astronomy, the Kepler's law of planetary motions was published by Johannes Kepler. It was published in 1609 and 1619, which was described the orbit of the planets around the sun. So here on the right side have the picture of the Kepler, and actually he published his first two laws about the planetary motion in 1609, and having found them by analyzing the astronomical observation of Tycho Brahe. And the third law, which was about the distance covered, and we are going to discuss, it was published in 1619. So what are those three laws? So just to give you an overview, so the first law of Kepler's was about the orbit of the planets is an ellipse with the sun at one of two foci. And the second law of the Kepler's about the planetary motion was a line segment joining a planet and the sun swap out the equal area during the equal interval time. So it states that every planet which is moving around the sun has the equal area. So I'm going to explain it when we are discussing in the detail. And the third law states that the square of the planet orbital period is proportional to the cube of the length of the semi-major axis of its orbit. Also, these laws the first law known as law of ellipses, and the second law is also known as law of equal area, because we are talking about the equal area, so about the equal area distance. And the third law is called the law of harmonies. So let's look at the first law, so which was the orbit of every planet is an ellipse with the sun at focus. So on the right side figure you can see here, so actually the orbit of the planets are not circular shape, but it's in ellipse shape. So it says there can be two focus of the one ellipse. So the one focus is here and the second one is here. And all the planets which is revolving around the sun are in ellipse shape. So at the time, this was a radical claim. The prevailing belief, particularly in the epicycle based theory, was that the orbit should be based on a perfect cycle, because most of the things which we look if has the gravity, so it's the circular orbit of the moving object should be in circular. But although an ellipse is not the same as a circle, as I mentioned, because circle should have the one focus, but ellipse has two focus, which is shown here. The most of the planet actually follows the orbit with low eccentricity, which means they can roughly approximate it as a circle. And the Kepler's calculations prove or demonstrate the truth about the planetary motion. So this was about the first law of the planetary motion. So it revolves in ellipses with sun at a focus. So this is one focus and this is two. So sun is still stay here and all the planets revolve around this sun. So let's look at the second law, which makes more sense to understand this first law. So he stated that a line joining a planet, so let's say this is the planet orbit, a line joining a planet and the sun swap out the equal area during the equal interval of time. And the planet move faster when they are near to the sun. So let's say if the planet is here, then it will move slow. But when it's near to the sun, it will move fast. So the same area is swept out in a given time. So let's say if it takes 1 day to move from P3 to P4, and also it takes 1 day from P1 to P2. So the planet will move faster here and be slower at this position. And obviously if it goes here, it will be more slower. So when the area of this triangular or these points can be calculated, so this area 1 and area 2 is actually equal. So that was about the second law of Kepler's about the planetary motion. And as I mentioned, it also known as the law of equal area. So this is quite understanding. And obviously when our planet is on this position, it moves faster. So that time we have the short of the days. And but if we goes here, then it's long of the day. So further explanation to this Kepler's second law versus Newton's predictions. So about a century later, 100 years later, Newton shows using his theory of gravitational. So that this is a direct consequence of conservation of angular momentum. So it can be shown that the angular momentum is proportional to the area swept out by the orbit of the planet. So as you know, the sun gravity accelerates when the planet is here in near. It accelerates the planet and come closer to the sun and decelerate when it is away or the way out from the sun. So however, since the Keplers predict the Newtonian gravity, he arrived at his conclusion empirically. So which empirically we are not going to explain here, but just theoretically I am going to explain in this part of the lecture. So now moving to the third law, so which is actually quite interesting law, which was proposed in 1619, sorry. It states that the square of the orbital period, which is the p square of a planet, is directly proportional to the third power of the semi-major axis. So in this case, let's say p square is your planet orbital period of the planet, and this is the semi-major axis. So it also implies that the period of a planet to orbit of the sun increases rapidly with the radius of its orbit. Obviously, when the planets move, let's say if the planet which we are considering is away from the sun, the radius of the planet will be increasing. So it compares the orbital period and the radius of the orbit of the planet to those of the other planets. So unlike the Kepler's first law and second law, which was describe the motion characteristics of a single planet, the third law makes a comparison between the motion characteristics of the different planets. So symbolically, we can represent the p square is directly proportional, which is the period of the orbital period of the planet is directly proportional to the aq, which is the third power of the semi-major axis. So over here, p is the orbital period of the planet, or we can say as a t, which I'm going to explain in the next slide. R is or the semi-major axis of the orbit. So the proportionality constant is the same for any planet which is around the sun. So you just have to put the planet, let's say if we have the earth over here, let's say if we put the p square earth divided by a cube of the earth, so which is the orbital period and the semi-major axis. So this is one of the graphical example in which actually we are showing. So let's say this is your Mercury planet and this is the earth, probably the Mercury, Venus, Earth is here. So must be Venus in between here. So let's say if we are calculating the ratio of the planetary motions, then we can say the R1 for the Mercury and R2 is for the Earth. And similarly, how much time it takes to revolve around the Sun is the time period. So also the time for revolving around the Sun for Earth is a different. So that's way we have to calculate for each planet. So if you can move to the Mars, Jupiter, Saturn, Uranus, Neptune, so these all can be done here using this relationship. So now this is a table which have been calculated already, so which observe that the t square over r cube ratio is the same for Earth as it is for the Mars, because Mars and Earth is quite closer. But if you look at the other planet, even every planet has the same the t square over r cube ratio. So let's start with the Earth. So let's say Earth has a period in year is actually 1 year. It takes 1 year to revolve around the Sun, and the distance, which is in astronomical unit, which is 1 light year. So this is also 1. So when we divide these two and put in this relationship or t square or r cube, so the answer will be 1. So it's the ratio is equal to 1. But if we move closer to the Sun, even it takes like 0.24 years to revolve one orbit, and the distance is 0.39 from the Sun, so still the ratio appears to be the same. Like Venus, you can see this one, and up to so on, like Mars and Earth has a close relationship. But if you look at all the table around this column, so you can see the ratio like Pluto, Neptune, Uranus, Jupiter, the ratio remains the same. So that's proof that the third law can be implemented, or it has been proven to the all planets. So that's all. I hope you have understand the 3 Kepler's law as a summary, or the introduction of these Kepler's law. Okay, thank you so much and have a good day.